The aviation industry is responsible for 2.5% of global CO2 emissions, and when considering its effects on atmospheric pollutants, that number increases to 3.5%. As economies grow and air travel becomes more accessible, these numbers are expected to increase significantly, and experts agree that the only viable path to net zero aviation emissions is through sustainable aviation fuels. But here's the challenge. In 2022, the US produced only 15.8 million gallons of SAF, less than the 1% of total aviation fuel demand. The Department of Energy has set a target of producing 3 billion gallons per year by 2030, and that requires a major leap in production. One promising solution is algae-based biofuels. Algae can produce 15 times more oil per acre than traditional fuel crops like palm oil without competing for farmland or for food production. It also captures CO2 directly from the atmosphere as it grows. However, the key question remains, where can we grow algae at the scale needed to power the future of flight? That's where our project comes in. We are Green Skies, a student research team working in collaboration with CleanJoule, a leader in SAF production, and Ken Labs, a geospatial AI company, to develop a data-driven AI-powered platform that identifies the best locations for algae cultivation. Our interactive website for site selection is called Algae Atlas, a tool that combines decades of climate data and satellite imagery, machine learning models to assess land suitability, and geospatial visualization to help make data-driven decisions. We've created an accessible, interactive platform that allows users to explore multiple tools to interact with historical trends and regional variations for growing algae. One of the key features is a total algae potential map, which allows users to toggle individual years on and off, displaying how biomass production has changed between 1979 and 2019. Clicking on bookmarks for California, Texas, Minnesota, and the mid-continental US lets users quickly zoom into specific regions of interest, and as users zoom in, the resolution automatically adjusts, providing detailed insights into algae suitability at different locations. To make long-term trends easier to analyze, this platform also includes an interactive slideshow that moves in 5-year increments from 1979 to 2019. Users can scroll forward or backward to compare time periods seamlessly. This makes it easier to track shifts in algae productivity over time. Since algae growth peaks during the summer months, Algae Atlas also provides a dedicated July algae potential map, which displays biomass production during the warmest season for key years at the end of 4 decades. This allows users to focus on how seasonal algae growth has evolved, particularly in regions with different climate conditions. To visualize how algae viability has changed over 2 decades, the platform features an interactive comparison slider, which transitions between July 1999 and July 2019 algae data. By moving the slider, users can see how biomass potential has increased or decreased in different locations. This feature is currently set to North Texas, highlighting regional trends in algae viability over time. Our interactive site selection dashboard brings together multiple data layers to support informed decisions for algae cultivation. On the left side of the dashboard, you'll find guidelines for identifying the ideal site based on the graph shown here. When you select a state or region, the dashboard displays a biomass productivity trend over time with a Thiel-Sen trend line that highlights whether growth is increasing, stable, or declining. An upward trend suggests improving conditions for algae, while a downward trend may indicate challenges. Alongside biomass, the temperature trend chart helps evaluate climate suitability. Warmer temperatures generally promote algae growth, but excessive heat can be a stressor. The Aware US water stress chart estimates available water after current demands, with lower values and green-colored areas signaling abundant water resources. We can also see the productivity insights for different regions in the US. This displays that the southern and eastern regions have a much higher productivity than the western and central. You can view specifics about the mid-continental US and see its average annual biomass, as well as a productivity gradient in latitude from the south to north. This reveals that productivity is higher in lower regions. By integrating these insights, the dashboard allows you to compare states and regions holistically. For example, if we take into account all these factors, Florida stands out as the best site for algae cultivation. It has a strong upward biomass trend, indicating consistent growth, stable temperatures, and low water stress, compared to Texas, which has high stress zones, limiting water availability. Florida's conditions are more sustainable for long-term algae-based SAF production. With the help of Andre Coleman and Micah Taylor at Pacific Northwest National Laboratories, this was created using ArcGIS story maps to display data from the Biomass Assessment Tool BAT. BAT predicts algae growth by analyzing light, exposure, soil quantity, and climate conditions. This tool transforms decades of data to support sustainable algae cultivation for the future of clean energy. Thank you.